let's start. So it will be like a bit of a private party. So thanks everyone for joining. It will be a bit of on advanced level about Kafka and Kafka Stream. So it would be good to understand who actually used Kafka and Kafka Stream before. Amazing, thank you, thank you. Only Kafka, it's good enough. So I think because this is like a bit of a private party, let's not ask a question at the end, because like it would be really better if you understand over the course of presentation what we're talking about. So feel free to raise your hand and we will give you words and you will ask questions and we will explain, because like, yeah, it would be good that message which one want to deliver will be actually delivered and you will understand what we're talking about. Cool, okay, let's start. So we are from TransferWise, as one of our values is like nothing to hide. So this is myself and Levani. I am an engineering in the payment processing team, and with me,
Levani. I'm leading the data streams effort at TransferWise.
At TransferWise, yes. Okay, cool. So, and we will speak today here about war stories about our adoption of Kafka Streams. And before starting talking about this, like just a couple of words for you to understand what is our business model and why we actually need it and what is it for. So TransferWise is a money transfer business, and it's why it is important because it actually adds a bit of like a flavor of how we are using data. For us, it's like really important not to lose messages. Deliver everything should be like eventually consistent, but consistent because it's money at the end of the day, what we are dealing with. So, and our logo, motto, slogan, motto, what we are working towards is money without borders, instant, convenient, and eventually free. So for Ukrainian customers, by the way, have someone used TransferWise here? Whoa. Thank you. So this is like for Ukrainian customers, how you can use it. You can actually transfer money to Ukraine from I think like around like 50 different currencies with, yeah, I've checked yesterday with our competitors, we are still cheapest option, which is quite good. Always pay attention to rate which you will get with your conversion, because it is important. Someone is hiding their fee within a rate. So this is our coverage, two-way. So this is the countries where we can send from and send to. And as you see, Ukraine is green, so at the moment we can send only to Ukraine. In numbers, because it is important, you need to understand with which kind of volumes we are dealing, what is the size of the company and size of data. So at the moment, TransferWise is around 1.6K employees, 4 million of users. We are transferring 3 billion pounds monthly. We're growing quite fast, 1% year-to-year growth, and this is not really important for Kafka Stream, but we are cash generating, so we are a profitable organization. From the technical perspective, how we are running our organization is we working in microservice-oriented architecture environment. We have 160 microservices, cumulative lines of code. Cumulative totals of lines of code on the backend is 3.5 million. So it's only backend without all the client sides. Around 300 engineers. And I don't know if you heard some presentations from us. We talked about like how we were modularizing, how we were killing our monolith. I can say that we did it. We slayed the monolith. It's still with us, but it's shrinking from Q1 of 2017, which is like very important milestone. And today we will talk about stream processing.
So now time is, after a very long day, to start talking about some interesting and hardcore stuff. So we will start talking about what kind of challenges we have faced while we were adopting the stream processing. So first, we will cover some operational challenges that we have seen with our Kafka setup, essentially what we have seen while we were setting up Kafka brokers for stream processing. Then we will cover a bit what we have done in order to get all the necessary data in order to do the successful stream processing at TransferWise. And then we will finally just sum up everything, how we are running all this machinery in production. So let's start with operations. So a couple of you have worked with Kafka, and in this section we will just cover of like what main problems we have seen with Kafka broker setup with stream processing in mind. So first, like very briefly with about our Kafka setup, we have quite moderate cluster. We only have 5 brokers for stream processing. It runs on AWS. It's M5X large machines, and it's like GP2 disks. We have 3 terabytes of GP2 disks for each broker. We will cover later why we need so much disk. So we use binary format, we use Avro message format for storing the data in the brokers, in the topics. And it's built with Confluent open source version, so it comes with Kafka 2.0. And like as Bohdan said, we are like very consistent with the data, so we have optimized for our brokers not to lose any data, so we have mean in sync replicas set as 2, and we have no unclean leader election. So essentially we have each event is replicated, is ensured that it's replicated at least 2 times. So like Kafka in general works very, very well. Like it's a known fact and it's been around for years, right? But stream processing is kind of new thing when you stream processing is essentially a new thing in Kafka ecosystem, more or less like new thing. And the main thing, main problem that we have encountered is essentially disks. What type of disk we should choose for storing the data on the broker side. So if you start like Googling or like seeing what to do, like what kind of disks to choose on AWS while setting up the broker, you will see that the most recommended one is ST1. And this kind of makes sense because like if you like read the docs of the ST1 and GP2, you will see something like this, that ST1 is optimized for high throughput and it's essentially optimized for log processing. And as we all know, the Kafka is like stores all the data as append-only log, so it kind of makes sense to use ST1, right? And then there is a GP2, which is like general SSD, like it's general purpose drive, so like not explicitly saying that it can be used for log processing. Then we have chosen ST1. And after running it in production, we have like encountered quite interesting things with it. So what happens now when we have ST1 and Kafka Streams in place? First, we have a Kafka Streams application which creates many internal topics. So Kafka Streams essentially is a framework built on top of native consumer producer clients, and in order to do the stateful stream processing, it creates a lot of internal topics to manipulate the partitioning, repartitioning, and things like this. So it creates many internal topics for your stream processing pipeline. So many internal topics translates to many partitions on a single broker. So essentially, we have already many partitions on one broker. And if you have many partitions, you're essentially getting random I/O and random small I/O. And if we see the docs of ST1, it's optimized for sequential reads and writes. And while we have many different partitions, essentially many different files on a single broker, it isn't really a sequential anymore. It becomes random. So and ST1 is like really bad with random small I/O. So we have seen quite bad performance of ST1 disks while working with the Kafka Streams applications. So our choice was like, we did some experiments. So we have experimented with different types of configuration. We even increased the native memory of Kafka brokers to help alleviate the disk problem, but it didn't help much. So we had to switch to GP2, and we have seen the performance gain like instantaneously. So it's like online operation. It don't have to do anything on AWS side really. You just go to console and change the disk size, disk type from ST1 from GP2, and you will get the results out of the box. So yes, the articles and everything have been recommending to use ST1, but in practice, when you have like not such huge amounts of data yet, and you have like many partitions on a single broker, it still makes sense to use GP2 rather than ST1. And so other broker configuration tips that we need to know while running the Apache Kafka in production, just to update the VM maxmap count config. So Kafka uses page cache and native memory quite heavily. And if you have many partitions on a single broker like we do, it writes a lot of data into native memory. So default max map count may not be enough, so you need to update it. Also, for sure, you need to update max open files, and in general, as more RAM you have, the happier Kafka you have, because you have the it can utilize its native memory and not to write disks that much. So
yeah, cool. We set up our Kafka stream cluster. We kind of know where to run it. We need to aggregate the data. We need to somehow deliver data there and start using it. And there are several approaches. One of the approach, both of them we need to look through perspectives that we are running microservice-oriented infrastructures, that we have a lot of microservices and we need to collect data from kind of a lot of them. One option, which again you will, if you Google, if you check, you will see that this is kind of one of the default solutions, is like you need to use Kafka Connect. Kafka Connect is a library which allows you to connect a lot of different types of data sources. So for example, you can connect it directly to the database and stream it to Kafka, and then basically whenever you want. So it will replicate your data storage to your Kafka streams, which sounds like an amazing solution, but it has some pros and cons. So if you're talking about pros, then basically all the streaming of data will happen automatically, and okay, not even automatically, but automagically, because it's quite a big library and quite a lot of data, if you imagine, from each and every service will be streamed through it, so it will kind of solve us a lot of problems with just one step. Also, what it's good at is that it's change data capture compatible. What does it mean is that it actually captures what is committed with each commit, what is committed, basically reads commit log and stream it to the Kafka cluster, which is amazing, which means that we're getting trustful data. But it also has some problems. One of them is it is a dedicated deployment which should be managed somewhere. It should connect somehow to the database. So we are what we are getting one database with several connections. And you know, in a microservice architecture, it's kind of a bad practice if you have more than one connection to one database. So you have this one here. Then you have, as for me, this is like one of the main disadvantages of this approach, is that you're actually exposing internals of how you are storing the data. And because in our case, when we are running microservices, we have around 50 teams, and teams own different set of microservices. And you actually not allowing a team to change data structure, because on a service level, teams are usually responsible for keeping their API backwards compatible, share the client libraries, and so that everything will work smoothly when you, for example, I don't know, calling some REST endpoints. But there is no such responsibility of keeping your database backwards compatible. So, for example, Kafka Connect will read it and actually replicate. And another disadvantage of this approach is it's requires quite a lot of platform type of work. So if you're talking about TransferWise, we have a ratio around 5% platform engineers versus, okay, 8% platform engineers versus rest of engineering. So this will put enormous pressure on this team, which is, yeah, and return of investments, as you see, because like there are a lot of disadvantages of this approach. So we started to think about other approaches. In our case, all the services which we are using have their own domain APIs. This APIs format, which I already mentioned. So, and they already talking through Kafka, because we're using Kafka not only for the stream processing, but we're using it just for internal communication, service-to-service communication. So why not to use these messages as a format, how data will be aggregated and communicated. So what are the benefits of this solution is that there is no magic. We are using exactly the same APIs. We have no coupling, so we're not exposing these internals of a microservices. We still have like one database per microservice, and it is less error prone because team owners have responsibility of keeping API backwards compatible. But there are some problems. One of them, like disadvantages, is that if you think about, if you just can't stream database with the previous solution, here you need to somehow build whole layer of solutions how to stream all historical data which you have in a database through the endpoints or through some kind of API to actually stream processing cluster. So this is kind of additional work which you need to do if you want to use this solution. And another thing is that even though API is backward compatible, but you need to treat your Kafka, the stream processing solution, as another consumer of your API. So you need to handle versioning, you need to upgrade it periodically and basically talk with the team what can be done there. So there are like still some downsides. And this is, for example, what we, at the end of the day, built and what we came up with, and this is how like data pipeline looks in our case. So for example, we have microservice with some database within a transaction. We are committing everything, sending semi-transactionally, we're sending data to our Kafka cluster. Let's call this Kafka cluster service Kafka cluster. So this is a Kafka cluster where service-to-service communication is happening. Then we have a separate layer of stream data collectors. So these are just like a regular consumers of same topics which we have for the service-to-service communication, which is doing some transformation, enrichment. Enrichment can be done, for example, through the API endpoints where for each message, for example, you are going and, I don't know, collect a rate for this particular, I don't know, bank transaction. And then at the end of the day, when we collected all the information, we streaming it to the separate cluster, which we set up just to keep information for stream processing. So at the end of the day, we built like 2 Kafka clusters, one for service communication, another for stream processing. So in our case, building these disadvantages which I mentioned about using of domain API, they were way smaller than using Kafka Connect. And in the long run, we believe that it's a better decision because of the stability of this solution. And in our case, we were a bit in a lucky state because we actually come to this microservice-oriented architecture, I don't know, like 3-4 years ago, and we already had events which sent by services as a source of truth. So already everything in the rest of the system was built based on the messaging. We haven't had any kind of we still have some, but they are not on a critical path. Like batch jobs which are going to the database and like, for example, processing, I don't know, like last 1,000 of something. So in our case, it was like easy. And I think like a logical question here will be why for collection of data, we decided to set up a separate cluster. So first of all, this was a bit of like a proof. It's still like a proof of concept. So we are trying to understand, is it a good technology for us? Actually, I think we understood already that it's good, but it took us quite a long time. And we decided to put it to the separate cluster just to first play it safe. We don't know how all this Kafka stream will load the existing Kafka brokers, so we just decided to separate concerns. Also, these brokers initially have very different SLAs. So for this, for service cluster, you can imagine, because like it's kind of backbone of our application. Everything should be fast, everything should be reliable, everything is monitored. If you're talking about this proof of concept, when we are offloading there a lot of data, SLAs there at the moment when we just started were like different. It shouldn't be like, I don't know, 3 nines or like 2 nines, 3 nines. 3 nines availability, it can be less just because we were testing this technology. So because of this, we did just like, this was another reasoning why we decided to put it a separate cluster. And another thing which we learned a bit in a hard way is that when you're launching with a Kafka Streams new aggregation, so for example, you had some, and you want to launch new one. To build a state, your aggregation need to go through whole history. And this process, apparently, is very CPU and memory heavy. So, and actually, we actually really lucky that we built it in this way because there is a possibility if you would build it on a regular cluster, it will just like shut it down because of the load, if all the consumers will start to rebuild states.
Cool. So now we'll cover what we have seen actually. Like we have covered like right now what we have worked and done with respect to actual streaming Kafka brokers. Now we will talk a bit of how it is like to run actual Kafka Streams application against the streaming Kafka broker. So to give you a bit of perspective and introduction, the Kafka Streams is a Java library, and it's not installed or run inside inside your Kafka broker. It's a just Java library that you can use or embed in your any like Spring Boot microservice, let's say, and this microservice is becoming your stateful stream processing kind of microservice. So this is how it's advertised, and it actually sounds very nice, right? So just put up some library, and it will become this kind of magical stream processing thing. But in reality and in production, when you have to run this, it's not that easy, and there are many pitfalls to take into account while running this in production. And now we will start covering what are those. So first, we need to understand how the domain events are produced at TransferWise. So TransferWise has been using the Kafka for quite some time, and it's not like new thing. And we heavily rely on Kafka. It's like our backbone. And to remember this like nice graph, and there is like this transaction thingy. So this is quite hard to actually do. And by design, you can't have this kind of two-phase commit between data source and Kafka. So you want to have this kind of thing reliably published. So whatever you have actually committed to your database, you want this change to be reflected in your Kafka cluster and not vice versa. So what actually the services do while they want to publish the events, they don't publish the event directly to Kafka. So essentially what we are doing when we have to like publish some domain event, we have, let's say, some business logic. We just do some kind of business logic magic, and then we essentially save outgoing event inside the database. So, and it's happening all in one transaction. So we are getting either we will do the business logic successfully and we save outgoing event that we want to publish all in one transaction, or we won't do anything. And there is separate process that actually pulls these outgoing messages, let's say buffered table that sends actually the events to the service Kafka cluster. So this is how the events are sent out to the service Kafka cluster. This gives us consistency between the database and actually between the service Kafka cluster. So we are sure that whatever changes are happening, whatever events are produced to the service Kafka cluster are actually happened in a transactional manner. In general, for financial institution, it's quite important as you can imagine, we are dealing with people's money, right? And it's super important not to lose any data. So everything at TransferWise has been optimized, and everything for TransferWise has been optimized for at least once delivery. So everything that we have built was optimized for this, essentially not to lose any customer's data and actually have the data delivered where it should be. So with this all reality, while you are like starting to build a stream processing kind of platform with this kind of events, you are kind of you are in a reality where actually you will get the duplicates, right? Because in these outgoing tables, there can be retries. The event was not published successfully, so this outgoing events table will just retry and send it once more. But maybe data was already in Kafka. So there are many talks of how the duplicate can end up in the Kafka. So we can search for this. There are many different interesting materials about this, but the reality is that with all this legacy code, as well as legacy systems that we have at TransferWise, as well as all this kind of consistency and all this at least once delivery semantics, we will get the duplicates, and this is the reality. Essentially, duplicate events are equal to corrupted state, right? So in the stream processing, if you have if you listen to some stream of events, and you are building, let's say, sum of profile lifetime volume. So how much money has particular user has transferred for the lifetime of TransferWise. So it's pretty easy, right? Nothing magical should be there. You just listen to this event, all the data is already in Kafka, and then you just aggregate just plus invoice value, and then boom, you got the result. And it sounds like quite easy to do, but when you actually dealing with the duplicate events and you can't understand if the event is duplicate or not, these kind of trivial things are not as trivial anymore, so they are becoming quite complicated. So now, like, we will try to cover of how we are actually not trying, but how we're actually doing the reliable deduplication with Kafka Streams. So this is like piece of code. So it's kind of a simplified version of actually what kind of code we are running in production as of now. So we have this kind of, you see there is like this nice, yeah. So there is this nice case stream. This is like kind of abstraction on top of the topic. So there is some kind of data inside the topic, and this is like case stream representation of the data that is inside the topic. So we are getting this transfer Avro events. So as we have covered, we are using Avro format everywhere in the streaming Kafka cluster. So we are getting this Avro data as a stream. And then essentially the goal of this is to listen to this event and aggregate the data on the fly. So now let's start covering this code a bit more into details. So we have this source. Now we want to cover. So now we want to filter out only necessary pieces of it. So in this case, we are only interested in the transfers that are submitting money to USD. So where the target currency is USD. So pretty easy with Kafka Streams DSL. You can just put the filter and it will do its magic. So it's like stateless operation, and it's super easy to do. Then what we are doing, actually we are building the state out of the filtered events that we have received inside the stream. So this is kind of, so we are not covering every bits and pieces what's happening beneath this whole code. You can, if you are interested, you can look up this for yourself. But the point of this example is to show how to do the reliable deduplication events in real life scenario. So if you will start adopting the stream processing in your organization and you have actually doing some kind of event publishing where you are where you can have the duplicates, this is the thing that most probably you will end up doing. So here we will just create a state out of this out of the event stream that we have filtered out, and what in this case the duplication logic is quite simple. So here in the lambda we have three parameters. First is the key, so the key of the event. Another one, second one is the value. So value that we have actually coming the current value of the event that we are receiving, and there is like the third parameter is the aggregate. The aggregate is what is inside the state already, so what we have aggregated so far. So the idea of this deduplication is if we have actually seen this kind of event before, so if we have actually seen this kind of transfer before, that means that it's a duplicate, and we will mark it as a duplicate and mark it to be ignored. So we have done this deduplication, then we will say that just filter out all the events that is marked as ignored. So we are just to sum it up, we are getting the events, filtering out all the we are filtering only necessary ones, and then we are just checking in the state store if we have already processed this event or not. If so, we are just marking it as a duplicate, and then we are proceeding. Then and the whole beauty of the Kafka Streams, and this is quite popular, to have this table stream duality. So every aggregate and every data that you're aggregating inside your state can be represented as a stream on its own. So here we are doing exactly the same thing. The aggregated data that we have actually stored on the disk and like checked that for the duplication, we are representing as a stream on its own. And then we have this nice deduplicated stream here available. So this is already processed events, already deduplicated, and now we can actually do the actual aggregations. So we have now this stream, and what we are doing now, we are just selecting the profile ID as a key. So in this example, we want to have the sum of invoice values per profile. Profile essentially is a user. And we are group by, and then we're doing the aggregation. So initial value is 0, and then we are saying that aggregate the profile volume, and boom, we are done. This was quite, the idea is like the aggregation is quite simple, right? But when you want to do it in production, when you want to do it in real life scenario, where you actually having the where you will actually have the duplicate events. This kind of trivial things are becoming not so trivial, and you will face the facts that you will have the bugs as well, not just the duplicate events. So when you're dealing with traditional SQL query, when you are doing like group by profile ID and sum of invoice value, if you have bug there, I don't know what kind of bug you can have there, but just if you have some bug there, you just tweak the query and boom, it will work, right? So nothing extra you have to do. But in the streaming world, it's not that simple, because every state that you have, every aggregation that you do is actually pre-computed state, and if you have done something bad inside your state, if you have some bug, so just one if statement that you have not put, or one filter that you have not put in your aggregation, that means that your whole state is corrupted, and you have to have a way to actually go back and replay. And the ability to replay is super important in stream processing. You just want to have this kind of flexibility of going back into the time and just starting from certain point and then just recreate your state from scratch. And this is why we actually have 3 terabytes of disk on every Kafka broker, because we store all the events in streaming Kafka cluster are stored permanently, so we don't apply any time-based retention on top of those topics. So usually, while in the service Kafka cluster, we have 1 week retention, so all the events are after older than 1 week is getting deleted by the broker. And while in the streaming Kafka cluster, all the events are stored in the compacted topics. So you can look what the compacted topics are. It's quite useful, especially in the stream processing. Yeah, so this is kind of the main idea of why we are actually saving all the events in our streaming Kafka cluster permanently. So we can have this kind of flexibility of actually replaying and recreating our state if we have some issues or if we want to have new aggregations. Another problem that we have faced is that at TransferWise we believe at continuous delivery of our software, and every service usually being released for like 2 or 3, maybe 4 times per day. We have like this rolling updates, so the release process of the Kafka Streams is not so trivial. So let's go to the example of what's happening when you actually do the rolling update. So imagine that we have this service, this Kafka, the stream processing service, and then you have like two instances of this. And each one of them has the data sharded, and the data is like distributed among two of those instances. So we do the release of one of them. Since like it's the release process, it's one of the consumers, essentially one of the native Kafka consumers, and then Kafka broker will see, okay, yeah, this consumer has gone down, is down now, so the data must be rebalanced. So whenever data is being rebalanced, it's a stop the world rebalancing. So everything is stopped at this point. So the data will be rebalanced to the still living consumer. The instance 1, that is where you are not releasing actually. And then it will say this, okay, Kafka will say to it, okay, one of the consumers has died. It doesn't know that you are actually doing just the release. You have just release process there. It doesn't know this. It just see that the consumer is down, so it will say to this active Kafka Streams instance, okay, just get this data because we need to replicate the state that was responsibility of the Kafka Streams instance that is being down. So it will recreate its state. And then at some point it will like, okay, I have all the data and now I can serve the traffic and I can send out the events back and I can serve the traffic as usual. But before this process has finished, you have a downtime essentially. Depending on the state, it may take minutes, it may take 5 minutes, it may take like a couple of seconds, so it depends on how big state you have. But the interesting part is this, that at some point this release, the instance that you've been releasing, it will come, it will be alive at some point and will say, okay, yeah, I'm here, give me some work. And Kafka will say, oh, cool, you are back here, take some partitions, and this will trigger, again, rebalancing. And here you have actually two rebalancing process in the Kafka Streams application where the data is sharded and you may be shuffling hundreds of gigs of data that we have seen in our production environment. So this, during one simple release process, we've been shuffling hundreds of gigs of data from one instance to another. And in general, achieving high availability is quite hard, right? So it's distributed systems. We have so many things around, and achieving high availability with Kafka Streams is even harder because in native microservices you have just microservices, and then you have some external database, and this database is just lives somewhere else. So when you reboot your microservice, nothing bad happens there. But with Kafka Streams, the data lives actually on the disk next to the Kafka Streams instances. So when you reboot it, you just have like the data lost, not lost, but the data is like unavailable for some amount of time. So high availability with Kafka Streams is even harder. So what we have actually, so the problem here is that we have one Kafka Streams application, right? They share the same application ID, essentially the same consumer group ID. So what we had to have some kind of way of having master and standby to achieve high availability. So we can actually first release on the standby cluster and then release on the master cluster. So this is what we have actually built. So instead of releasing on one of the instances, we have clustered instances now. So this same fraud application, the fraud Kafka Streams applications, now is divided in two parts. One of them acts as a master, one of them acts as a standby. They are exactly the same applications, just different consumer group IDs, application ID in a Kafka Streams terms. So and we release only on standby. It does all the necessary balancing. Then we release on master, and then it's switched. And where you have released, it's switched as a master, so it serves then traffic. And then you just release on standby. So this is how we are actually achieving high availability with Kafka Streams. In general, besides this, with
this is mine already. So yeah, this is all interesting, and as you saw, that there are a lot of things happening under the hood when you are doing like quite normal processes like releasing and, for example, reprocessing, so which puts Kafka Streams in quite unique positions. That like all the nodes when you are running, 5 minutes, all the nodes when you are running Kafka Streams will need a lot of RAM, will need additional CPU, will need some special disks, as we already covered, that like not all the disks will work with it. And if you're working, for example, like, I don't know, on Amazon or something, you need to consider how much of IOPS you need. So before the Kafka Streams, our microservices were kind of similar. So it's like same application with this database. We're using Spring Boot. So we have more or less the same requirements. And what is it? Come on. Okay, cool. Yeah, no, yes. What's happening? Amazing. So what we have is like each microservice was relatively same. So we have for all the 160 microservices, which you can multiply by 6, which is a number of instances, relatively same machines. But if you start use Kafka Streams as a library, as it's actually promoted, each of the microservice will become a unicorn because you need a lot of resources to it. And adding Kafka Stream as a library, it's not like, I don't know, you will add a JSON parser, which will give you some new capabilities, how you can do it faster, better. It's adding a lot of different requirements for this machine. So one of our main learning was that it's not so easy. It's not just a library, and you need to understand what kind of computing power, RAM, and disk you will need for these microservices. That is why, to avoid such unicornish setup in our organization, what we decided to do, we decided to group all the stream processing services which we have into the platform. So we are not using Kafka Stream as a library, which is actually promoted as one of the advantages of this approach, of this technology. But we actually building platform. So how does it look is that we have an application, which is, on the left we have this aggregated data. This is aggregated data, historical data without retention, It's consumed by the set of services which is, we know that they're unicorns with special resources. And at the end of the day, results of this processing publish it back to the service Kafka cluster. Remember, this is this cluster which is used to service communication. So for regular services, they kind of know nothing about this unicornish setup and everything, all this aggregation is happening kind of under the hood for them. So to build a platform, we're needed to define some ownership model, how teams will cooperate. In our case, we build, it's quite simple, this is our GitHub. As you can see, this is like actual GitHub picture, where we have for each pipeline we have at the moment, for each team, we have a separate Gradle module. So we are compiling them separately. They have some common components which allow us to do quite nice things. So for example, we can configure, it's quite easy for new team to come in and start using Kafka Stream. Also, we can allocate different resources we can understand how much resources is needed. We can allocate between these modules how much is used by which module. And also, as you saw, we have solved some problems, like, for example, releasing and deduplication. And to provide it as a platform for these 50 teams and 300 engineers which we have in the TransferWise, it allows us to increase speed of adoption of this platform. So because we're already providing these building blocks of the Kafka cluster, of the stream processing. And one last thing I will just briefly mention, that there is such term, reconciliation. Who heard it in the, you're working somewhere in finance, yeah? Like in financial startups. So yeah, reconciliation is like almost a swear word in our company because everyone hates it. Reconciliation is when you need to check that one data source is actually kind of have the same information as another data source. And if you saw in our picture, we have actually 3 different data sources. We have microservice database, which is, we can say it's source of truth for this microservice. So because it will return API calls to this microservice, will return information from the database. Then we have this service Kafka cluster where service-to-service communication is happening. This is another source of truth. And the last one is where we have all the historical data of all domains which we need for stream processing is in another Kafka cluster. So we have 3 different states which we need to understand. Do we have some bugs? Like maybe something is, I don't know, duplicated, or we have miscalculated something. And again, we are dealing with money, so we need to be really careful there. So we built another module, especially for this, for these needs. What it does is it's actually on the periodical manner just go and check state which we have in this aggregated data cluster with the source of truth, with actual APIs. So we're checking consistency of data, and we're checking existence, that like all objects have which we have in the Kafka stream, they presented there, and vice versa. Problem is that it's quite heavy process. Again, you cannot use it if you're using Kafka stream is just a library. No, you need additional resources for this. And also another kind of layer of protection which we have is we are using Snowflake. Who know what a Snowflake is? Okay, Snowflake is a kind of a database, high-performant one for analytical queries, which know how to work with a lot of data. So in our case, what we are doing, we're actually replicating some business logic which we have in the stream processing later on in the Snowflake queries. So what we are doing, we are doing some aggregations. We are pushing them to the service Kafka streams. You kind of saw this flow already. And also then we push it to the Snowflake. And then we're actually checking that data which we have in the stream processing is actually same as Snowflake results which it give us. It's kind of give us some basically place where we can write group by. Snowflake is analytical platform. It doesn't provide any kind of, you cannot use it for operational needs. So you cannot replace Kafka streams just with a Snowflake because it's a heavy process of loading data there, queries, yeah, so it's not replaceable. This is mostly for analytical purposes. And another way how we are ensuring that our data is correct in the at the end of the day we have correct data, is that we are releasing data first to standby cluster only, the thing which Levani already explained. We are giving it some time, so the data from this standby cluster will be published to the Snowflake, and then we can compare standby cluster data with actually real cluster data, which is running at the moment as a master. A lot of overhead, but as a financial institution, we have to do it because of reconciliation. And summary.
So we have covered like dark side of the Kafka streams in this talk, but in general, stream processing is hard. You have to deal with reconciliation, you have to deal with high availability, and many, many different things that we don't really have time to cover in this talk, but there are many different things that needs to be taken into account. And our main point of this talk is just to say that Kafka Streams is super amazing library that gives you like huge possibilities of building the amazingly performant applications that can do the real-time aggregations, which are quite complex problems to solve, especially when you want to transfer money instantly and you want to do the 10 million, okay, not 10 million, but many fraud checks and make sure that everything is legit with the transfer. So these kind of things, when you want to do it in under 1 second, is quite hard problem to solve. And Kafka Streams actually gives you possibility to solve these kind of problems in real time. In general, Kafka Streams is one building block. If you will adopt it, you will start building many different building blocks in order to make it production worthy. You will start thinking about how to do reconciliation, how to deal with this, how to do some different operational tools, etc. We have built different kinds of operational tools, even internal library to actually run the Kafka Streams inside the TransferWise, inside our Spring Boot application. So we have done quite some amount of work in order to ship it into the production. But community is amazing. The work with Kafka Streams is ongoing, and the community is super active. So there are quite, I don't know how many are you familiar with terms of KIP. So it's essentially Kafka improvement proposal. So there are quite important KIPs submitted that are being worked on by the community already. So there are KIPs that promise to solve this stop the world rebalancing. So this thing should go away soon. So we will hopefully get rid of this standby and master cluster. I'm not so sure about this, but I still hope. And there are many different improvements that are still coming into the Kafka stream. So it's amazing library. It's super useful. It really works, and it gives amazing performance. But you will start dealing with a lot of headache as well. Just good things doesn't come without a price in general. So this is kind of our main message here. And we're hiring. If you want to work with the Kafka Streams, don't forget about us. And yeah, thank you for attending.
Without this, no. Okay, thanks. Have you ever considered scaling that deduplicator stage in your processing pipeline?
Because it's like Bob will bounce back. Can you define scaling, please? I will repeat them to Mike. Yes. Of course, we are running more than one. We are running a lot of them.
So like the internal state is part of the application. So what we are running, this deduplication layer, is just one part of the aggregation. It's not like separate Kafka Streams instance or anything. It's just one, essentially one topology that runs through this. So every aggregation that we have and every team pipeline just needs to go through the deduplication. So we don't have this like common pipeline of deduplication which every team uses. So because we can't, every team thinks about the duplication differently, and they have different kind of logic, as well as operational, as well as logical deduplication. So there are many different deduplications that the event should go through depending on the need. So it's just one step in the aggregation process. So it's not like different pipeline or different Kafka Streams instance. Does this answer your question? Okay.
Yes, we did, but like it doesn't matter because like +1 message means, I don't know, +1,000 paid out on some bank account, for example. So cost of mistake is quite high, so we have to do it. Yeah, it's not because of Kafka, it's because we are working with 2 data sources, one which is within the service and another which is Kafka by itself. So it's kind of, it's not a problem of Kafka, it's a problem when you want to have more than one storage and you want to kind of keep it synchronized, you need to optimize for something. And in our case, logical was, choice was optimizing for at least once delivery. Okay, cool. Yes, please. Yes. Can you repeat, without which purposes? Okay, okay, yeah. It's internal. It's internal where we're actually running all the aggregation. It's just like, just to illustrate that we platform work with the Gradle modules, like, yeah. Yes, there are plans, but we are going through the adoption. It's a very good question. It's a very good kind of push for us to share the knowledge, but yeah, we just wanted to share here like a logical way how we are doing it. I mean, like the workflow, but second step will be actually code. But I don't got the first one.
Yeah. So there are, like, we started work. So our services are moving to Kubernetes, and we actually have moved to Kubernetes. And in Kubernetes, we are using Kafka to log all the Kubernetes logs are going through Kafka cluster, but it's like separate Kafka cluster, and it's like used for only for logging. So we use Kafka for that as well. Yeah. So we have actually we have 4 Kafka clusters. Fourth is security Kafka cluster, which we don't know nothing about, and only security team knows. Mm-hmm. Mm-hmm. Yeah, that's a very good question. Thanks. So right now we don't move it anywhere. We do all the compaction. So we just store the latest state of the given key. So let's say for a certain transfer ID, we only store the latest state for this transfer. So we just do compaction, but we don't apply time-based retention anywhere. And we don't move, at least for now, we don't move our data anywhere to S3. There is one of the keep with Kafka, which actually introduces the external storage to the Kafka. So the idea is to have real-time part of the topic, which like couple of segments. So let's say for the last 3 segments will be real-time, and the rest will be backed by a remote storage. So this is ongoing work in the Kafka community to actually introduce the out-of-the-box external storage. But right now we don't move the data, so it still resides in Kafka. Yes. No time-based retention. It's stored there permanently.
8 years, I think you're asking about, yes?
Ah, you're asking this. Okay, I don't know.
I think like as financial institution, we have to store data for 8 years. This is what you're asking about? Yes, yes, we are doing it. Yes.
Actually, it's not filling up that fast, just because we still apply compaction and we use Avro. And we just don't store the JSON string, so this gives us room. So it fills up, but it doesn't fill up that much. So our current rate is, if I'm not mistaken, 0.3% per broker per 2 weeks, I think, just something like this. But we have, like, with AWS, it's, like, yeah, of course, costs money, but we can just scale it. Yes, yes, we do. Yes. So we have built internal. We don't use. So the plan is to use the cruise control. This is one of our roadmaps, to have the cruise control in place, since we already have, like, the cluster grows and it will grow in the future. So we just want to invest time in this. But we have built this platform. Actually has this admin client inside of it, and it has some kind of predefined commands as the configuration. So it does all the necessary administration on its own. So it manages the Kafka broker setup, like topic creation in advance and things like this. So it uses just admin client API and does its magic.